This is section 9.2, the central limit theorem for sample means. We turned to simulations in the previous examples because the number of possible outcomes was too numerous to handle. There are still two questions that need to be answered. Are these approximated sampling distributions similar to the actual sampling distribution? Yes, since the sampling methods were random and many repetitions were done, and the results of these sampling are the results of these simulations predictable? The answer again is yes, which means that we do not need to run a simulation to know what the sampling distribution will look like. Instead, a mathematical theorem called the central limit theorem gives us a very good look at the very good approximation of the sampling distribution. We are going to be using the version of the central limit theorem that applies to sample means today. We used the version that applied to sample proportions in chapter 7. This version can be used when the following conditions have been met. So this is when we're talking about X bar. So we're looking at sample means. These are the conditions that the central limit theorem needs. The sample is collected randomly from a population and the observations are independent. So they're random samples and they're independent of each other. This sample can be collected with or without replacement. Condition number 2, the sample size n is large enough, or, so n is large enough, or the population distribution is already normal. So typically the cutoff is 25. We're going to check to see is n greater than or equal to 25. We will look at a population that is not normally distributed in today's group activity. And condition number 3, if the sample is collected without replacement, then the population size n, notice the population is the capital N, must be 10 times bigger than the sample size. And we can check this condition by multiplying our sample size by 10 and seeing that it's less than our population size. So this is only necessary when we have sampling without replacement, but oftentimes you don't know whether it's with or without replacement. So just to be on the safe side, we'll just check condition number 3 and then we don't have to worry about it. If these conditions are met, then the sampling distribution for X bar has a shape that's approximately normal. Okay, so we're going to know that our sampling distribution looks something like this. The normal model becomes more and more accurate as your sample size increases. So for a big sample size, we're really close to normal or normal. And if our population is normal, already normal, then we're normally distributed. A mean that's equal to our population mean. So we have this shape. We know that it's going to be centered around mu. And the standard deviation is going to be sigma over the square root of n. So most often we won't know sigma because this is a population parameter. And so we'll want to estimate sigma. And we can do that by using S. Okay. So that is our estimated standard error. So the central limit theorems for a sampling distribution for X bar is approximately normal with mean mu and standard deviation sigma over the square root of n. So we can write this out on our graph here. So here's the picture of our distribution. The shape is normal. It's centered at mu, which means that we'd have mu plus sigma over the square root of n. And if we go up 2 standard deviations, we have mu plus 2 sigma over the square root of n. Or mu, if we go 3 standard deviations. And also we could go the other direction, down 1 standard deviation. and down 3 standard deviations. So the key features of a sampling distribution is it is the probability distribution for a statistic. It shows all the possible values of the statistic on the horizontal axes. So this is our sampling distribution. These are X bars. So X bars can range anywhere from plus or minus 3 standard deviations away from you. It gives us the probability of each possible statistic. This tells us how often we can expect to see particular values of our estimator. And it gives us important characteristics of the estimator, such as bias and precision. Bias is measured using the center of the sampling distribution. It's the distance between the center and the population value. Precision is reflected in the spread of the sampling distribution and is measured by the standard deviation of the sampling distribution. The standard deviation of a sampling distribution is called the standard error. And it is a measure of how much our estimator typically varies from sample to sample, or how far our estimators typically are from the mean. The smaller the standard error, the more precise our estimator. It is used for making inferences about a population. So let's check to see if the central limit theorem would have correctly predicted the sampling distributions from our previous simulations. So we had the results from our simulations, and now we're going to use the central limit theorem. Remember, we ran 3 simulations in which 1,000 random samples were collected from the population of a mother's height, which was the population was mu, mean 62.5 inches, and sigma was 2.4 inches. So in simulation 1, the following is approximated sampling distribution for X bar when we take the simple random samples of size n equals 10. The population had 1,375 mothers, and we recorded the mean height of each sample. So let's check the central limit theorem's 3 conditions to see if they are met. So first, 1, were they randomly sampled and independent? Yes. They're a random sample and independent. So oftentimes you'll see me write simple random sampling was used and ind for this. 2, what was our sample size? Our sample size was n equals 10, which isn't quite big enough to meet the sample size condition, but it came from population that was normal. So that this was met. We had simple random sampling in independence. We had a normal population. And 3, we want to know, was our population more than 10 times our sample size? So 10 times 10 is equal to 100, which is less than 1375. So that also has been met. So we can use our central limit theorem. Yes. And what does our central limit theorem say about our shape, center, and spread? It will tell us that it is approximately normal. So it's approximately normal with mean mu. So it's going to be centered at 62.5. And it's going to have a standard deviation of sigma over the square root of n. So let's calculate the sigma over the square root of n. And that is equal to 0.5 0.76. And you can see that that's pretty close to what we're seeing in our simulation. So if we were to draw the distribution, we'd say, okay, it's approximately normal. It's centered at 62.5. And then we can go up 1 and down 1 standard deviation. And so if we label up 2 standard deviations and 3 standard deviations, we can see that this spread is very similar to what we're seeing over here in the simulated histogram. Okay, so did the CLT accurately predict the results of the simulation? Yes, it did. Its shape was agreeable, center, yes, and spread. So the conditions were met, and then when we applied it, we saw that it did predict the simulation. Now let's look at simulation number 2. The following is an approximated sampling distribution for X bar when we take a simple random sample of n equals 25 mothers from a population of 1375. And we record the mean height of each sample. It is an approximated sampling distribution in this case, since it contains the results of simulation with 1,000 repetitions or samples. Let's check our CLT's 3 conditions. 1, did we have simple random sampling? Yes. And independence. 2, was n is equal to 25, which is greater than or equal to 25, and our population is normal, so we met both of these even though we only needed 1. And 3, is n times 10 less than 1375? The answer is yes. This would be 250, which is indeed less than 1375. So we've met our 3 conditions. Yes, we can use the central limit theorem. Now, what does it tell us? It tells us again that our shape is going to be approximately normal. It's going to be centered at 62.5, and that we're going to have a spread, the standard deviation is going to be sigma over the square root of n. Sigma over the square root of n. So in this case, we're looking at 2.4 divided by the square root of 25, which is equal to 0.48. So we're saying that our X bar are approximately normal with mean 62.5 and sigma square root. So let's try that again. Standard deviation of 0.48. So this is a very close match to what we're seeing from the simulations. So yes, again, it does predict what we saw in the simulations. Let's check our 3rd simulation. So again, same scenario. This time we have a sample size of n equals 50. So we're having 50 mothers. We're sampling them 1,000 times, calculating the mean of each sample. And again, each of these, checking these conditions, they're similar. We still have simple random sampling and independence. Check. N is equal to 50, which is greater than or equal to 25, so yes. And 3, n times 10 is equal to 500, which is less than the 1375. So we've met all the conditions. We can use the central limit theorem, and the central limit theorem tells us that we expect to see an approximately normal with its centered at mean 62.5. So our X bars are going to be approximately normal, 62.5, with a standard deviation of 2.4 divided by the square root of 50, which is equal to 0.34. And again, this is matching well with what we're seeing in the simulation. So yes, the CLT does predict our simulation. To summarize, in each simulation, all three conditions were met. Each simulated sampling distribution is very close to the normal model predicted by the central limit theorem. The central limit theorem correctly predicted the shape, the mean, the standard deviation of each sampling distribution. The precision increased as the sample size increased. In other words, the standard error decreased with larger sample size. In a real-world application, we usually only take one sample from a population and calculate one X-bar. Keep in mind that the bias and precision are both measures of what would happen if we could repeat our survey many times. We won't know the value of sigma. How will we calculate our standard error? Well, we could get a pretty good estimate of the standard error by using S, our standard deviation of our sample, in place of sigma. This is called the estimated standard error and is a useful approximation to the true standard error. Just a reminder, a probability tells us how often an event will occur if we repeat an experiment an infinite number of times. This means that the sampling distribution for X bar gives us probabilities of where our sample means would fall. That is, how often we would expect to see a particular value of X bar if we could repeat our sampling infinitely many times. It also tells us how likely it is that we will find an X bar within an interval, how likely it is to find an X bar greater than a particular value, or how likely it is to find an X bar less than a particular value. So, knowing this, let's look at some examples. Some sources report that the weight of a full-term newborn baby has a mean of 7 pounds and a standard deviation of 0.6 pounds, and they are normally distributed. Draw the normal model for this population distribution. So if we have a population, these are parameters, and we just learned that mu is equal to 7 and sigma is equal to 0.6. Be sure to include the mean and the mean plus 1, 2, and 3 standard deviations, as well as a title for your horizontal axes. Okay, so let's draw this distribution. We can label this with weights. And so any given weight, or X, let's call it, is normally distributed. Our weights are normally distributed with mean 7 and sigma 0.6. Use the normal model for the population distribution to find the probability that a randomly selected baby weighs greater than 8 pounds. So let's first mark that on our picture. And the probability is asking us about finding a baby or randomly selecting a baby that's out here in this tail that's more than 8 pounds. So how can we calculate this? We want to first standardize our 8 pounds. So we would say the probability that X is greater than 8 is going to be equal to the probability that Z is greater than something. So let's figure out what Z we're talking about. We have our value minus our mean over our standard deviation. So we get 1 over 0.6. which equals to 1.67. So we're interested in finding out what's the probability that Z is greater than 1.67. So when we're using a greater than, that's the number that we look up, the 1.67 on the chart, is going to give us the probability of being less than 1.67. So we would do 1 minus 0.0475, which is equal to 0.9. Oh, I just wrote that wrong. Let's try that again. 1 minus 0.9525, which is equal to 0.0475. So the probability that a randomly selected baby has a weight of greater than 8 pounds is 0.0475. Now, suppose we take random samples of 100 babies. Can we use the central limit theorem to create a model of the sampling distribution for X bar? So first, before we apply the central limit theorem, we need to check those conditions. Condition 1, simple random sampling and independence. So suppose we take a random sample. We'll assume that they're all independent. That one has been met. Does n greater than or equal to 25, or is our population normal? So our n is equal to 100, and they told us our population was normal. We definitely met that one. And 3. Is n times 10 less than our population size? So n is 100 times 10 is equal to 1,000. And our population, we're wondering, is this going to be less than n? Our population is all babies. So yes, 1,000 is definitely going to be less than all babies. So we have met our 3 conditions, and now we can actually apply the central limit theorem. So the central limit theorem says that our X bar is going to be normal. It's going to have mean mu, which is 7, and standard deviation, that's sigma over the square root of n. And in this particular case, that's 0.6 over the square root of 100, which equals to 0.06. So we can now draw this distribution. So when we draw the distribution, we want to make sure we're labeling that this is a distribution of sample means, our X bars. They're centered at our mu 7, and you can see now that they spread from 6.82 to 7.18. Use the normal model for the sampling distribution to find this probability. The probability that a random sample has the mean weight of 8 pounds. Notice the difference in the language here between this question and the one up here. Up here, we had a randomly selected baby. We were talking about an individual baby being selected, and versus down here, now we're talking about an average, finding a mean weight. So if we took a sample of 100 babies, what's the probability that we'll actually see an X bar that's greater than 8? So looking at our picture of our distribution, where is 8? Well, it's probably not even going to fit on my paper. It's somewhere like over here. And what's the probability that we're going to be finding an X bar that's greater than that? So pretty small. We're going to expect a very small number, right? So let's go through how would we calculate this. So this is the probability that we'd find an X bar that's greater than 8 is going to be equal to the probability that Z is greater than, and we need to calculate our Z. Z is equal to 8 minus our mean over our standard deviation. And so we come up with 16.67. So the probability that Z is greater than 16.67. If we were to try to look this up on the table, we're basically going to see that this would be 1 minus 1, the probability that Z would be less than 16.67, which will be basically 0. So when they're talking about sample means, and the distribution of a sample mean is when we want to check our conditions for the central limit theorem. That's what we did here before we actually apply the central limit theorem and find out our new standard error. Okay, that's the end of section 9.2.